We can go.
Oh, okay. Hi, I'm Mahi.
Hi, I'm Janice.
We're on the sensor development sub-team in spring 2021. So first, I'll give you a brief overview of what SensorDev does. Our goal is to create low-cost sensors to be used on-site and in the lab for operators and researchers to gain some insight into the process of water treatment. And we work on many different types of sensors. Previously, the team has developed turbidity sensors for the HRS team and created sensors for operators to check the heights of sludge blankets and worked on one for dissolved organic matter. And the main goal of SensorDev is to gain insight into the various processes of the Agua Clara water treatment process to identify inefficiencies in the system.
So the sensors development team this spring focused mainly on the dissolved organic sensor or the low-cost turbidimeter worked on from past semesters. We are continuing the experimental setup from last fall, which includes using different sources of light powered from an Arduino board to measure the sampled dissolved organics within the water samples. We are currently testing the visible light RGB sensor, and after we will move on to fixing the IR sensors and compare the three based on cost and efficiency. Since there were errors in data collection from fall 2020 and this spring, we plan to prioritize fixing the wiring of the board itself and getting better connections from the board to the sensors, since the wiring was very poorly connected to the tape.
So more specifically about the dissolved organic sensor, it uses water samples from different stages in the plant in order to determine the quantity of dissolved organics. And this quantity then corresponds to the amount and type of coagulant to remove these particles from the water. And the context and relevance of dissolved organic sensor is that sometimes at Agua Clara plants, the incoming water source could be discolored because of certain dissolved organic matter. And so the plants need sensors for that organic matter to determine if there are certain particles that the turbidimeter won't see. However, commercial dissolved organic sensors are quite expensive because they use UV wavelengths, but we're trying to work on a cheaper alternative that uses 450 nanometer blue light instead.
So since dissolved organics in the water treatment plants are not always visible using a turbidimeter, we need another device that detects the organic matter. And so by using different light sources like the RGB and IR sensor based on a 90-degree angle scattering, it allows both color and detection of the dissolved particles. And the photos show how the RGB sensors work, and there's a transmission of light through the sample liquid and a detector that reads the light that is transmitted. And the reason that it's placed at a 90-degree angle is to take into account the possible variety of sizes of the solid dissolved particles. And the particle size will taint the distribution of the scattered light and place the receiver in a 90-degree angle from the emitted. And furthermore, we would have a sensor present 90 degrees from the light source in order to measure the light that was reflected, and a sensor parallel to the light source in order to measure the light that was absorbed.
So this image shows the specification for the sensors for the infrared and for the blue light that were 3D printed. And their setups only differ slightly, with the RGB sensor having slightly smaller spaces for the sensors than the IR based on the shape of the sensors itself. So basically, LED light produced from one end of the casing will go through the water sample to a light sensor, and then this will record the intensity of the light transmitted through the sample. And then another sensor will be set up 90 degrees from the path of the produced light to record the intensity of the scattered light at the sample. And at low turbidity, the scattered light will also be low, but will increase as the turbidity increases. But dissolved organics are difficult to measure using slowly transmitted light, so the contrast of the scattered light recording gives a more accurate measurement of the contents of the sample. And so that's why our sensor has two parts, the blue light, which would measure organic matter, and the infrared light, which would measure the turbidity, and measuring the intensity at 90 degrees and directly across from the source.
So this model of the turbidimeter determined in spring 2019 will have two sensors, one directly across and the other at 90 degrees from the light source. And this will measure the light scattered by the particles at that angle. So as the turbidity increases, the scattered light will increase and only some of the light will be transmitted. But at a very high turbidity, the amount of scattered light will also decrease due to absorbance. However, the transmitted light would roughly be the same due to limitations in measurement. And having the second sensor will help us get a better picture of the situation. The implementation of the turbidimeter will lead to more accurate readings and analysis of the turbidity using the infrared sensors.
So this is a circuit diagram for the phototransistor, and the circuitry for the visible light source is basically the same as that of the other project, and this design has been consistent for multiple projects. So the only thing that we've kind of altered was which Arduino input pins we're using the circuit, because we hypothesized that the pins or the board were slightly faulty, and we have been testing moving things around, but the logic of the circuit was the same.
Sorry. So this is the setup of the dissolved organic sensor with the Arduino board wired to the casing that contains the water sample. You see the green light is our RGB LED light that is used to measure the absorbance and transmittance of the coagulants in the fluid. And the sensor is also wired at the side at a 90-degree angle. And we basically insert the water sample vial in the case with the light source on one side and the sensor on the other.
So these are some images of data results for running the tests on the 0 milligram per liter and 1000 milligram per liter water samples with the kaolin clay dissolved in them. And this is with the visible light setup. So these numbers are a lot lower than the numbers that we got, that fall 2020 got when they were trying to use the IR setup. But we still see no clear trend because the numbers for both 0 and 1000 milligrams per liter are very similar. Also note that the transmitted numbers are all zeros because we only set up one part of our sensor when taking this data, and we only set up the scattered. And we still expected that there would be some kind of trend, but we're unsure if maybe connecting the transmitted will give us a better picture of what the trend is when using the visible light. But another reason that we think that these numbers might not show a clear trend is because there are a lot of like outside sources of error. For example, the light in the thing wasn't very secure in its position, and neither were the sensors. So there could have been, they could have been placed at an angle, or there could have been outside light coming into the reading that could have altered the numbers that we see on our screen. So moving on. For the future tasks, we want to basically finish fixing up the visible light sensor and then use this sensor to measure the turbidity of samples with varying concentrations of clay dissolved in the water, not just 0 and 1000. And then we're going to try to compare these results to turbidimeters given on the market and produce a kind of calibration curve. And then hopefully the IR sensor once we have the proper parts and figure out how to actually wire the sensor. Yeah, that's basically all.
So thank you. That concludes our presentation. If you have any questions, here's our emails. And here are the appendix slides. Yeah, okay, thank you.